Electric field of multiple charges. Since the electric field of a single charge is a vector, the electric field of multiple charges may be calculated by adding, point by point, the electric fields due to each charge. The addition is not carried out by just adding the magnitudes of the individual fields. It must be done by adding their vectors, with vector addition. This is the electric field configuration due to two like charges. There is no electric field midway between the two like charges. The individual electric field vectors cancel out. The shape of the field is the same for both positive and negative charges. Only the field direction is different. So, you could think at this point, there's an electric field due to this charge that points this way. At that point, there's also an electric field that points this way due to this charge, and those cancel out. They add up to 0. This is the electric dipole configuration, consisting of two unlike charges. There are no places where the electric field is 0. Again, the shape of the field is the same for both positive and negative charges. Only the field direction is different. So, let's take a point in the middle. The electric field at the middle due to the positive charge is to the right. The electric field at the middle due to the negative charge is also to the right. So you end up with a field vector that points directly across from positive to negative. Electric dipoles appear over and over again in studies of the atom and molecules. Water molecules are electric dipoles, and this helps explain how microwave ovens cook food, the high surface tension of water, and why water is a universal biological solvent. Later in this course, magnetic dipoles will be discussed, and these have crucial applications. Net electric fields will now be calculated mathematically, and for more than just a pair of charges. The net electric field is the sum of all of the electric fields at that location, where n, here, little n, is the total number of fields present at a location. The direction of each electric field will determine the signs used here. Our objective is to find the net electric field at the origin for this charge configuration. So this is the location we care about. Mark the point on the sketch where the electric field is to be calculated. So that's what I've done here. It's this point right there, the origin. Draw the electric fields acting at that point. So, these are all positive charges, which means the fields due to those charges will point away from them. So, the field due to charge 1 will point to the right, away from charge 1. The field due to point 2 will also point to the right, away from charge 2. This charge, however, its electric field is going to the left this way. So here are our three electric field vectors. Calculate the magnitudes of those vectors, the magnitude of the electric field, these vectors here, assigning negative values to fields that point to left. So this is going to be a negative value. These will be positive values. And then we're going to sum them up and find the net electric field. Let's work this problem now with values for the charges. So we have these three positive charges located at different locations on the x-axis, and they each have values. So positive 9.1 microcoulombs, which is the same thing as times 10 to the negative 6. So let's go to the next slide and do step 1. Step 1 is to mark the point at which the electric field is to be calculated. So here in red, the red dot is at the origin. That's the point we're interested in. Step 2, draw the electric fields acting on that point due to all three charges. So, remember the field due to this charge over here, the field points away from this charge like that. So, at this point, we'd have a vector pointing this way due to this charge. Over here, we have a vector pointing this way due to the first charge. We have another vector pointing to the right due to the second charge. So let's see. All right, cool. So this is kind of like a free body diagram. It's showing the vectors of the electric fields and the directions that they point. Step 3, calculate E1, E2, and E3, assigning negative values to fields pointing left and positive values to fields pointing to the right. All right, so the magnitude of electric field due to a point charge is kq over r squared. So for the first charge, we're going to have this little vector here, and we're going to plug in all our info, right? So 9 times 10 to the 9th, that's k. The charge of q1 was, I don't remember what it was, but you know what? We can just pull this out here. So here we have all our values. We have k, and then we have 9.1 times 10 to the negative 6 coulombs, and this charge is 8 units away from the origin. So that distance is 8 meters, and that needs to get squared, and you end up with 1.3 times 10 to the third newtons per coulomb. Now this is going to have a positive value since it's pointing to the right. So this is the length of this vector. We do the same thing for the other two electric field vectors. So for E2, we have a vector pointing to the right, so it's going to be positive. K, we have our charge here. This point charge is only 2 units away from the origin, so therefore we put 2 in for the distance, and that also gets squared, and it's going to be positive, so we have 6.8. You can see that the field due to this charge is much larger than the field due to this charge, and that's because of the distance, right? We have that inverse square. So if you're farther away, the field will be much smaller. All right, and finally we have the field due to charge 3, and we plug in our numbers, we get our magnitude, and it's going to be negative since the field due to that charge points to the left. Step 4 is to sum the individual electric fields. So here, we're going to sum them up. So here you can see we factored out that times 10 to the 3 because that was in all of the terms. And it's very important that this 1.5 has that negative sign since the electric field due to charge 3 points to the left. You add them together and we get an overall net field of 6.6 times 10 to the 3 newtons per coulomb to the right.